All right, I want to walk you through the first two problems here. I had a little trouble with the video editing software, so I've done part one here, and you can see the solution to get the force between the Earth and the Sun using Newton's law of gravitational attraction. That's pretty straightforward, but I'm going to talk about number two, where I actually put in the numbers to get the speed of the Earth around the Sun. So the force that makes that happen is the force we calculated up here, and rather than using this number, I'm going to actually write out the equation again. And then since Earth goes in a circular orbit around the Sun, we're going to assume that, at least to approximate it that way. We have mv squared over r. Now mass of the Earth cancels on both sides, and one of the r's cancels too. So when we want to calculate this, we can actually do a simpler calculation. 6.67 times 10 to the negative 11th times 2 times 10 to the 30th divided by 1.5 times 10 to the 17th. All of this under a square root should get us the speed of the Earth around the Sun. So we're getting 6.67 10 to the negative 11th times 2 times 10 to the 30th divided by 1.5 times 10 to the 17th. And if we take this, all of this, under a square root, we're getting about 29, and getting about 30 meters per second as our answer. Something about that doesn't sit right with me, but these are the numbers that I'm getting. So I'm going to put a big question mark here. I just don't trust these numbers. Check them yourself and just let me know what you get. And we can talk about this a little bit later. Now, the orbital distance of a geosynchronous satellite, we had actually talked about this particular question. So we have an orbital period of 24 hours. So keeping this in mind, let me just check one more thing, okay, before I move on. Okay, so I had that right too. 2 times 10 to the 30th kilograms. The last thing to check. Yeah, okay, so I'm working with accurate information here. I don't know what's up. All right, so this is what I have for this. And then, because the answers I'm seeing online and in other sources say it's kilometers per second, which would actually be 30,000 meters per second. So I'm off by a factor here, and I can't seem to find the exact source of error. It's a little frustrating. So last thing to check, let me just make sure I've got Earth's gravitational, so universal gravitational constant. Yep, got that right too. Okay, so this is the Earth's mass. We'd actually done this calculation in class. I'm going to be a little bit strict here. I'm going to actually ask you to find this in your notes. If you want to look it up online, let's actually get you a quick value for the number. I just want to make sure that you're sort of doing the work and checking it with me. So geosynchronous orbit value in meters. Yep. So it says 2,236 miles. So hang on, and then good. So let's just good. So you should end up getting, when you get the answer, it should be about 4.2 times 10 to the 7th meters. Around that number. and we can double check that together in class too. All right, deriving Kepler's laws to estimate the mass of the Earth. So let's do the following. Kepler's laws basically say the force of attraction between the Earth and the Moon. We start off with Newton's law of gravitational attraction. So we got mass of the Earth, mass of the Moon over r squared. And then the effect of this is that the Moon goes in a circular orbit around the Earth. And then the other thing we want to remember is that v is 2 pi r over t, since we're moving in a circle. So let's cancel a couple things. The mass of the Moon cancels out, and one of our r's cancels out too. So I have g, mass of the Earth, divided by the distance from the Earth to the Moon, equals v squared, like this. Now I'm going to substitute g me over r equals, now I'm going to square the v, so that's 4 pi squared r squared over t squared. Let me bring the t to the other side. And so what this is going to give me is that t squared times g, mass of the Earth, over r equals 4 pi squared r squared. Next, I'm going to divide both sides by r squared, so that'll put an r cubed here. And lastly, I'm going to divide this out on both sides, so I wind up with t squared over r cubed equals 4 pi squared g over the mass of the Earth. Now this is true for the Moon going around the Earth. It's true for any set of satellites going around a mass. So now what we can do is we know that the Moon's period is 27 days, and this is its distance. We need 27 days converted into seconds. So t is 27 times, that's 27 days. There's 24 hours in a day and 3,600 seconds in a day. And then the radius, the distance from the Earth to the Moon actually, is 3.84 times 10 to the 8th. So what I'm assuming is you should get something on the order of 6 times 10 to the 24th. So go ahead and finish that problem and let me know if that's what you get. So that is it for the circular motion and astronomy practice test.